Okay, this is the second half of lesson 5D. Here's the homework from last night. Okay, so let's get right into today's lesson. Now we're just talking about the difference, the sampling distribution of the difference between two means. We had a similar lesson at the end of 5C about the difference of two proportions. So this is difference of two means. So the mean is just if you're subtracting x1 minus x2, the mean would be the mean of the first one minus the mean of the second one. The means are pretty much exactly what you think is going to happen. Like there's nothing unusual. The standard deviation, however, is a special formula. Again, you want to do square root of the first standard deviation squared over n plus the second standard deviation squared over n. As long as both samples, so you have to check the less than 10% condition for both sample sizes, which is kind of interesting here. And then finally, it's a normal if you check the large counts condition. In this case, if both sample sizes are at least 30. So with means, they have to be at least 30 for the central limit theorem to kind of kick in there. So that's how it works. These are on the formula sheet. Okay. Fast food restaurant uses an automated filling machine to pour soft drinks. The machine has different settings, small, medium, and large drinks. According to the machine's manufacturer, when the large setting is chosen, the amount of liquid L dispensed by the machine follows a normal distribution with a mean of 27, standard deviation of 0.8. When the medium setting is chosen, it has a different mean and standard deviation listed there, but it's normal. To test this claim, the manager selects independent random samples of 20 cups filled using the large setting and 25 cups used filling the medium setting. So the mean setting of the large one minus the mean of the medium one be the difference in the sample mean amounts under two settings. Assume the manufacturer's claim is true. Is the shape approximately normal? So what you would need to do at this point is, let me get this out. So it's actually pretty quick, right? So it says, so the 1 cup is 20 is N, and the other one is 25. So is the shape of it normal? So they both have to be at least 30. It doesn't look like it passes, right? So this is interesting, right? So it doesn't pass by the central limit theorem. They're not at least 30. But if you read the question carefully, right, it actually told us each individual population was normal. Yep, that one's normal, that one's normal. So if you subtract, that was one of the theorems we learned a couple sections ago. If they're both individually normal, if you subtract, the result's going to be normal, right? So yes, it is, even though it doesn't do it by the large counts condition, right? So even though it doesn't pass that, it is normal. When the large setting is chosen, the amount, okay, so forth. So test this claim, where do you write that? Calculate and interpret the mean of the sampling distribution. So the mean would just, you get your calculator out. And let me grab this over here. So the mean was X, the large one minus the small one. So the large was 27. So 27 minus 17, I believe. So it's a mean of 10. So if we take all possible samples of size 20 in the large lids, and all possible samples of size 25 and the medium lids, and we find the difference of the mean difference in the large lid minus the small difference, the average will be 10. Let's see what it says. 10 ounces, I guess I should have said. Yeah, that's the basic idea. Just include context of the problem. I think we're at the same way. Calculate and interpret the standard deviation. So standard deviation is, I believe it's square root of a fraction. So it's the first standard deviation squared, so 0.8 squared over, I think that one was think N was 25 for that first one. Let me check. 20 for the large cups. Okay, sorry. Okay, so divided by 20 plus standard deviation squared, which is 0.5 squared, divided by, I think that one was 25. I think that should be right. We should check the 10% condition first, right? So that's one thing I did not check. So 20 is less than 10% of all the cups that are filled using the large setting, and 25 is less than 10% of all the cups filled using the small setting. During that whole week at the restaurant, you'd have many more people than that. Then you calculate the standard deviation, and then you interpret it, right? So if we took all possible samples of size 20 for the large cups, all possible samples of size 25 for the medium cups, for the mean amount of liquid found in there, then the typical variation from the mean, typical variation from the mean is 0.205. Let's see what they said. Typically vary from the mean difference in the population means by about 0.205. That's your lesson for today. There's a few more example problems. And so you can just kind of go through this. Is this approximately normal? Let's see if we can do the test for this one or not. At a laundromat, there are two types of washing machines, standard capacity and large capacity. The length of time S it takes for a standard capacity machine to complete a regular wash cycle is a mean of 45 minutes, standard deviation of 3. Length of time L for a large capacity machine to complete a regular wash cycle is a mean of 60, standard deviation of 4. It doesn't say they're both normal. I haven't seen that yet. During 1 year, the laundromat owner chooses a random sample of 40 wash cycles from a standard capacity machines and independent random samples of 40 wash cycles from a large capacity machine. Let that be the difference in the mean amount of time to complete a regular wash cycle for two types of machines. So is it normal? So what do we need to check here? So a random sample of 40 for the first one and a random sample of 40 for the second one. So 40 is greater than or equal to 30, 40 is greater than or equal to 30 for both things. So because 40 is greater than 30 for both of them, it is approximately normal by the central limit theorem. Calculate and interpret the mean of these sampling distributions. So you're just going to subtract the means in the order they said. It's X, so it's S minus L there. So mean of 60 for L and mean of 45 for S. So that'd be 45 minus 60, which is negative 15. So negative 15 minutes. If we took all possible samples of size 40 for the regular wash cycles and 40 for the large capacity wash cycles, the result or the difference in the sample mean times would be an average of negative 15 minutes. Use the context of the problem there. Finally, verify both types of independence in the settings and calculate and interpret the standard deviation. So we've got to do the less than 10% condition. So 40 is less than 10% of all. S stands for standard capacity washing machines, and then L, 40 is less than 10% of all large washing machines. And then you find the standard deviation using the formula. So square root of 3 squared over 40 plus 4 squared over 40 is 0.79 minutes, which means if you want to interpret it, we take all possible samples of size 40 for the standard washing cycles and all possible sample sizes of size 40 of the large capacity washing machine. The resulting difference